Hi guys, welcome to my channel, Nerd Talk. I'm excited to share this video with you. This is part 1 of our video series, Formation of the Universe and the Solar System. We will explore the incredible journey from the Big Bang to the creation of our cosmic neighborhood. The universe began as an extremely tiny, dense, and hot point of energy about 13.8 billion years ago. This point rapidly expanded in what we call the Big Bang, starting the universe's expansion according to general relativity. Albert Einstein's general relativity shows that space-time is dynamic and can expand. This explains that the Big Bang was not an explosion in space, but the expansion of space itself. Right after the Big Bang, quantum field theory explains the high-energy universe transformed into fundamental particles. Quarks combined to form protons and neutrons, which fused into simple nuclei like hydrogen and helium. As the universe continued to expand and cool, about 380,000 years later, electrons combined with these nuclei to form neutral atoms. This process released radiation known as the cosmic microwave background, marking the moment when the universe became transparent. After atoms formed, gravity began to shape the universe. Small density differences in matter gradually grew, pulling gas into dense regions. Over time, these dense regions collapsed under gravity to form the first stars. These were the building blocks of the early cosmos. Inside these first stars, nuclear fusion began, producing light and heavier elements. This enriched the universe with the materials needed for future cosmic structures. Groups of stars came together to form galaxies, including our own Milky Way. Over billions of years, galaxies clustered into a vast cosmic web, creating the large-scale structure of the universe we see today. The formation of the solar system progressed through several key stages, starting with the solar nebula and leading to the eventual setting of the stage for planet formation. About 4.6 billion years ago, a gas and dust cloud in the Milky Way collapsed under gravity to form the solar nebula. Most material centralized to form the sun, while the rest flattened into a rotating disk. Most of the material concentrated at the center, forming the sun, while the remaining gas and dust spread out in the surrounding disk, setting the stage for planet formation. Within this rotating disk, tiny particles of dust and ice began colliding and sticking together through a process called accretion. Over time, these formed larger bodies known as planetesimals, which further combined to create planets. However, not all material became planets. The leftover debris remained as smaller bodies, such as asteroids, comets, and meteoroids, which continue to orbit the sun as remnants of early solar system formation. Dust accretion led to the formation of planetesimals, which further combined to create planets, resulting in our early solar system with an asteroid belt, comets, and meteoroids. In the early solar system, collisions between asteroids and comets were common. These impacts shaped planetary surfaces and may have delivered essential materials like water and organic molecules, influencing planetary evolution. We now focus on the solar system, our planetary home, which formed from the solar nebula about 4.5 billion years ago. The solar system includes 8 orbiting planets, divided into inner terrestrial planets, which are rocky, and outer Jovian planets, which are gas and ice giants. Beyond the planets are leftover materials like the asteroid belt, Kuiper belt, and Oort cloud. The sun is a massive sphere of hot plasma, primarily hydrogen and helium, driving thermonuclear fusion at its core. This fusion releases the light and heat that make life possible on Earth. Internal structure of the sun. The sun has a complex layered structure, with each layer playing a unique role in producing and transferring energy. The core, fusion center. This is the innermost region where nuclear fusion occurs. Hydrogen atoms combine to form helium, releasing an enormous amount of energy that powers the sun. Radiative zone energy produced in the core moves outward through this layer in the form of radiation. It can take thousands to millions of years for energy to pass through this zone. Convective zone here. Energy is transferred by convection. Hot plasma rises toward the surface, cools down, and sinks again, creating a continuous cycle like boiling water. Photosphere. This is the visible surface of the sun that we see from Earth. It emits the sunlight and heat that reaches our planet. Chromosphere A, thin layer above the photosphere, visible during solar eclipses as a reddish glow. It is hotter than the photosphere. Corona, the outermost layer of the sun's atmosphere. It extends millions of kilometers into space and has extremely high temperatures, much hotter than the surface. Gravitational dominance, containing 99.8% of the solar system's mass, its gravity keeps planets in stable orbits. It generates a powerful magnetic field, heliosphere, shielding us from cosmic radiation. The sun is currently in its stable main sequence phase, where it generates energy by fusing hydrogen into helium in its core. After billions of years, as its hydrogen fuel gets exhausted, the sun will begin to expand and transform into a red giant, growing so large that it may engulf the inner planets. Eventually, the outer layers will drift away into space, forming a glowing shell of gas, while the remaining core will collapse into a small, extremely dense object known as a white dwarf. This marks the final stage of the sun's life cycle, where it will slowly cool and fade over time. The sun's structure includes 6 main layers: the core where fusion occurs, the radiative and convective zones, and the outer layers like the photosphere, chromosphere, and corona. The sun's life begins in a stellar nebula, evolving into a protostar with a rotating disk. It then stabilizes as a main sequence star, where hydrogen fusion burns for about 10 billion years. When hydrogen runs out, the sun will expand into a red giant, potentially engulfing inner planets. It will then shed its outer layers as a planetary nebula, leaving behind a dense white dwarf to slowly fade. Scientists study the sun through major space missions. These advanced missions help us understand solar activity, solar wind, and space weather, which is crucial for predicting solar storms and their effects on Earth. Missions like Ulysses provided the first 3D views of solar wind, while SOHO studies the sun from its core to the outer atmosphere, helping observe multiple solar cycles. The Genesis mission collected solar wind samples, and Stereo uses 2 spacecraft to create 3D images for tracking solar storms and predicting their impacts. Hinode investigates the mystery of the hot solar corona. The Parker Solar Probe is the closest spacecraft to the sun, traveling directly into the corona to collect groundbreaking data. The solar orbiter captures detailed images of the sun and studies its polar regions. India's Aditya L1 is positioned at the L1 point, studying the solar corona, wind, and space weather. The upcoming Punch mission, a group of satellites, will provide 3D observations of space weather, studying how the sun's corona transitions into solar wind. Now we begin our exploration of the planets, starting with the closest to the sun, Mercury. Mercury is the smallest planet and fastest, orbiting the sun in just 88 Earth days. Its surface has extreme temperature swings due to the lack of an atmosphere, ranging from 430 degrees Celsius during the day to minus 180 degrees Celsius at night. This image highlights the unique characteristics and extreme environment of Mercury, the innermost planet. Naming. Mercury is named after Mercury, the swift messenger of the Roman gods, reflecting the planet's rapid motion across the sky. Potential for life. The environment on Mercury is extremely harsh, with intense heat, cold, and solar radiation. These conditions make it highly unlikely for life to exist on this planet. Size and distance. Mercury has a radius of about 2,440 kilometers, making it just over 1/3 the size of Earth. It is located approximately 58 million kilometers from the Sun, or 0.4 astronomical units. Sunlight takes only about 3.2 minutes to reach Mercury. The infographics detail Mercury's highly elliptical orbit and slow 59-day rotation. It has no moons or rings, a rocky, cratered surface, and a massive metallic core. It possesses a thin exosphere and a weak magnetosphere. Orbit and rotation. Mercury has a highly elliptical orbit, ranging between 47 million kilometers and 70 million kilometers from the Sun. It completes one orbit in 88 days and rotates on its axis once every 59 Earth days. Interestingly, one full day-night cycle on Mercury, solar day, lasts 176 Earth days. Its axial tilt is just 2 degrees, so it does not experience significant seasons. Moons and rings. Mercury has no moons and no ring system. Formation of Mercury. Mercury formed about 4.5 billion years ago from gas and dust pulled together by gravity. It is a terrestrial planet with a rocky structure similar to Earth. Structure. Mercury is the second densest planet after Earth. It has a massive metallic core that makes up about 85% of its radius. This core is partially molten, surrounded by a thin mantle and crust. Surface features. The surface of Mercury resembles that of Earth's moon, filled with impact craters formed by collisions with meteoroids and comets. Large basins like Caloris Basin were created early in its history. The planet also has long cliffs formed as it cooled and contracted. Bright streaks called crater rays are formed by debris thrown out during impacts. Temperature extremes. Temperatures on Mercury are among the most extreme in the solar system. Daytime temperatures can reach 430 degrees Celsius, while nighttime temperatures drop to minus 180 degrees Celsius due to the lack of an atmosphere to trap heat. Water on Mercury. Despite its proximity to the Sun, Mercury may contain water ice at its poles. This ice exists inside permanently shadowed craters where sunlight never reaches, allowing extremely cold conditions. Atmosphere. Exosphere. Instead of a thick atmosphere, Mercury has a very thin exosphere made of atoms like oxygen, sodium, hydrogen, helium, and potassium. These particles are constantly blown away and replenished by solar wind and micrometeorite impacts. Magnetosphere. Mercury has a weak magnetic field, about 1% the strength of Earth's. Despite this, it interacts with the solar wind to create magnetic storms and magnetic tornadoes that send charged particles toward the planet's surface. Due to its proximity to the Sun, Mercury is one of the least explored planets. So far, only 3 major missions have been sent to study it. Mariner 10, the first spacecraft to visit Mercury, used a gravity assist from Venus and performed 3 flybys. It mapped nearly half of Mercury's surface and discovered major features like the Calorus Basin. Messenger was the first to orbit Mercury, mapping the entire surface and discovering its large metallic core, unusual magnetic field, and evidence of water ice at its poles. Bepi-Colombo, a joint ESA/JAXA mission, is the most advanced mission yet. Expected to orbit in 2026, it will further study Mercury's composition, structure, and evolution. Next, we move to Venus, the second planet from the Sun and Earth's closest planetary neighbor. Venus is the third brightest object in the sky, rotating slowly and in the opposite direction of most planets. Its thick carbon dioxide atmosphere traps heat, making it the hottest planet, with surface temperatures up to 467 degrees Celsius. Venus was named after the Roman goddess of love and beauty. Surface features are mostly named after women. It is nearly the same size as Earth, orbits at 0.72 astronomical units, and has a dense cloud cover. A Venusian day is longer than its year, rotating backward in 243 Earth days. It has no moons or rings, though it has a temporary quasi-satellite named Zuzve. Venus formed similarly to Earth, but evolved to be extremely hostile. Venus has a rocky structure similar to Earth's, an iron core, rocky mantle, and thin crust. Its surface is dominated by volcanoes, deep canyons, and unique features called tesserae, reshaped by intense volcanism. The atmosphere is mainly carbon dioxide and sulfuric acid clouds, causing an extreme greenhouse effect. Unlike Earth, Venus lacks a strong internal magnetic field, having only a weak induced one. Exploration missions have been crucial for studying Venus, which remains mysterious due to its thick cloud cover. These missions have revealed its scorching surface and active geological features. Mariner 2, the first mission to another planet, confirmed Venus's extremely hot surface. Venera 7 was the first to land successfully, confirming high temperatures and crushing pressure. Venera 9 sent the first images from the surface, revealing a rocky landscape. Venera 13 captured the first color images and analyzed soil, surviving for over 2 hours in the extreme environment. The Pioneer Venus mission studied the atmosphere and cloud structure. Magellan used radar to map 98% of the surface, revealing detailed volcanic features in geology. Venus Express studied the atmosphere, suggesting Venus may have once had oceans. Akatsuki currently orbits Venus, focusing on weather, cloud movement, and atmospheric dynamics. Some pictures of Venus' surface and atmosphere. This concludes our look at Venus's surface and atmosphere. We will continue our exploration of the solar system in Part 2. Thanks a lot for watching, and be ready for Part 2.